Hey everyone, and welcome to the Sleepy Explainer. Tonight we're going to drift gently into the story of stars, how they're born, how they live, and how they finally fade away. Close your eyes for a moment and imagine a sky full of tiny glowing points, each one carrying a long history, each one quietly shaping the universe around it. For the next 2 hours, I'll be your guide through this slow cosmic journey, spoken softly so you can listen, learn a little, and hopefully relax enough to drift off to sleep. If you'd like, you can tap the like button, subscribe, or even whisper in the comments where you're watching from and what time it is where you are. Now settle in, take a deep breath, and let's begin with the calm beginnings of a star's story. In the quiet stretches of the universe, far beyond the warmth of nearby suns and the circles of known planets, there float enormous clouds of gas and dust, so large that they can span hundreds of light years, and yet so thin that if you could somehow stand inside one, you might not even notice the faint grains drifting past you. These clouds do not announce themselves with light or sound. They hang almost invisibly in the dark, only revealed when the faint glow of starlight filters through, or when the pressure of nearby events makes them shimmer faintly against the black. They are called nebulae, a word that simply means mist, and that is exactly what they are. Vast cosmic mists stretched across the night, fragile in appearance, but strong enough to hold within them the raw materials from which stars, planets, and eventually life itself can emerge. A nebula is made mostly of hydrogen, the simplest atom, joined with helium and sprinkled with tiny amounts of heavier elements like carbon and oxygen, and within it also float microscopic specks of dust, each smaller than smoke, each carrying with it the memory of long-dead stars that lived and died billions of years before. To the eye they look like silent smudges, but to the patient mind they are libraries of possibility, places where the past is stored and the future is prepared. If you could drift across one, you would see nothing move quickly, but over millions of years they shift and stir, like breath moving through lungs on a timescale too slow for human senses. They are shaped by gravity's quiet hand, pulled gently by the unseen attraction of their own mass, and sometimes sculpted by the winds of nearby stars or even the echoes of explosions that once shook the region long before. They are not empty, they are waiting. And this waiting is not aimless, for inside the stillness tiny variations always exist, a region just a little denser than its surroundings, a spot where the gas has gathered more closely, a knot where particles huddle together as though whispering to one another in the silence. That knot will pull in more of its neighbours, and those neighbours will gather more, and over time the cloud that seems so static will begin to form patterns, ripples, invisible seeds of change that will slowly but surely grow heavier. These ripples are the first hints of stars. But to understand the pace of this story, you must let go of the way humans measure time. The changes are so gradual that whole civilizations could appear and vanish while a cloud still looks exactly the same to the eye. From the perspective of the universe, however, the clock is always ticking, and in these clouds, every faint pull, every drifting particle, every small imbalance is part of the long countdown to a birth. It is in these clouds that our sun once began, long before the earth circled it, long before oceans and forests and people existed, and it is in clouds like these that countless other stars wait for their chance to shine. Imagine for a moment the oxygen you breathe, the iron in your blood, the calcium in your bones. Long ago all of those atoms rested inside a nebula just like this one, floating quietly, patiently, as if asleep, waiting for gravity to call them into a new form. Nebulae are not simply clouds. They are the nurseries of the cosmos, cradles that hold silence until the first cries of starlight are ready to be heard. For now the cloud rests, dim and hushed, spread across distances so great that even light, racing at its unimaginable speed, would need hundreds of years to cross from one side to the other. Yet deep within its depths, hidden from ordinary sight, the process of gathering has already begun. A patch grows slightly warmer, slightly denser, though still invisible to all but the most sensitive instruments. The rest of the cloud does not notice, but this subtle difference is the spark of a chain of events that will eventually reshape the darkness. And so, the nebula remains, outwardly calm, a soft and silent sea of gas and dust, but inwardly alive with potential, carrying within it the quiet beginnings of the stars that will one day light the sky. Inside the silent cloud, where atoms drift with almost no pattern, and dust grains float like faint specks in endless night, gravity begins its quiet work. Gravity is invisible, it has no colour and no sound, yet it is the patient thread that ties the universe together. In a nebula, this pull starts small, in regions where the gas is just a little denser than the rest. That tiny difference is enough for gravity to gain an advantage, for in those slightly thicker patches the particles tug at one another more strongly, and as they gather, the pull grows stronger still. It is a feedback that never stops. The more mass that gathers, the more powerful the attraction becomes, and the more powerful the attraction, the faster more matter drifts in. To us, this process is beyond slow. On human scales, it feels frozen, but in cosmic time it is steady, inevitable, unstoppable. Imagine a snowball resting at the top of a hill, rolling ever so slightly downward. At first it is just a small lump, unnoticeable, but as it moves it gathers more snow, it grows heavier, and its movement pulls in more of the hillside around it. Gravity's pull inside the nebula is like that, only stretched across millions of years and distances so vast that even light takes centuries to cross from one side of the clump to the other. The hydrogen atoms within the clump begin to collide more often, no longer drifting endlessly apart, but brushing, bumping, striking gently, raising the temperature within the growing knot. The rest of the nebula still seems calm, a quiet canvas across the sky, but hidden inside, warmth is building, pressure is rising, and the clump that began as almost nothing is slowly shaping itself into something with weight and presence. These clumps are called condensations or cores, the earliest seeds of stars. Not every clump succeeds. Some are too small, and though they gather material for a time, they never become heavy enough to continue the story. They fade back into the cloud, dissolved by turbulence or scattered by nearby winds. But others cross a quiet threshold, pulling enough mass into themselves that they can no longer be stopped. Their own weight presses inward, their centre becomes dense, and their outer layers fold ever more tightly around them. It is not violent, it is not fast. It is as though the universe is slowly folding a blanket, drawing it tighter and tighter, until it no longer lies loose but takes on a new form. As this continues, the clump grows hotter, not yet a star, not yet shining, but glowing faintly in infrared light, a kind of hidden warmth invisible to human eyes. If you could drift nearby in a ship, you would not see a glowing sun but a dark, dense knot of gas slowly breathing inward, gathering strength. Across the nebula, this may be happening in many places at once. Dozens of clumps forming, hundreds in larger clouds, each one shaped by gravity's hand, each one a potential star. Some may grow into small red dwarfs, steady and gentle, others into yellow suns like our own, and a few into giants that will live fast and die young. But here, in the stillness of the cloud, all are simply beginnings. The gas flows slowly inward, the dust settles more closely, and gravity pulls with endless patience. It does not rush the story, for time is on its side. It will wait 1,000,000 years or 10 million if needed, always gathering, always pressing inward, until the weight of the clump becomes too much to resist. And in that weight lies the next step of the journey. The cloud is no longer entirely silent. Deep inside, hidden from view, the soft heartbeat of a new star is starting to build. As gravity pulls more and more of the nebula inward, the dense clump at its centre no longer behaves like a simple gathering of gas. The weight pressing down is enormous, and that pressure turns into heat. Every particle that falls inward collides with others, and each collision adds a little more energy to the heart of the collapsing cloud. Over millions of years, the temperature in the core rises higher and higher, until the knot that was once no different from the rest of the cloud begins to glow from within. This glowing seed is called a protostar, a word that means the very first star, not yet fully born, not yet ready to shine in the way a mature star does, but already separate from the formless cloud that surrounded it. To human eyes, this object would not yet be visible, for the thick blanket of gas and dust around it hides all ordinary light. But if we could see in infrared the wavelengths of heat, we would notice a warm ember forming, glowing gently in the darkness like a coal buried beneath ashes. The protostar grows by feeding on its surroundings. Every strand of gas drawn in by gravity falls onto it, adding more mass, pressing the centre tighter, raising the temperature further. Around the forming star, material that does not fall directly inward begins to flatten into a spinning disk. This disk is wide, thin, and faintly glowing as it rotates, carrying countless particles of dust and ice that will one day build into planets, moons, asteroids, and comets. At this stage, a solar system is not yet recognizable, but the ingredients are already in place, turning slowly, quietly, in the shadow of their central protostar. The star itself is restless in these early years. It is not yet stable. Streams of gas can be flung outward from its poles in narrow jets, shining faintly as they cut through the surrounding cloud. The surface of the protostar ripples and shifts, expanding, contracting, adjusting to the enormous forces acting on it. It is a newborn in the truest sense, learning how to hold itself together. Sometimes the collapse is too fast and the star swells, releasing energy in short bursts. Other times the pull of gravity dominates and the star contracts again, growing denser, hotter, closer to the threshold it must eventually cross. All the while, gravity remains relentless. It keeps pulling gas inward, feeding the young star, making it heavier, hotter, and brighter in the wavelengths of light we cannot see. Millions of years may pass like this, and yet the process continues steadily. From a distance, the nebula still appears much the same, a drifting patch of dust and gas across the galaxy, but hidden within it, the protostar is preparing. It is still wrapped in its cocoon, still invisible to ordinary sight, but inside that cocoon, change is accelerating. The heart of the star is becoming denser every moment. The pressure is immense, pressing the atoms so close together that their energy builds toward a tipping point. Once that point is crossed, something new will begin, something that will turn this hidden object into a true star. For now, it is not quite there. It is still a protostar, fragile yet powerful, waiting for the moment when the heat inside becomes great enough for hydrogen atoms to fuse. That moment, the beginning of nuclear fusion, is the final step in star birth, and when it arrives, the protostar will no longer be hidden. It will shine with its own light, steady and clear for the first time. The nebula, once a silent cradle, will release its child into the galaxy. Our own sun once passed through this same stage, long before Earth existed, long before any living being could look up and see its glow. The protostar years are the quiet preparation, the gathering of strength, the struggle before balance, the ember before flame. And as we leave this stage of the story, we move closer to the moment when the spark of fusion will ignite and turn the protostar into a star that can truly shine. Every protostar begins its life not in isolation but within the larger womb of its parent cloud, and this is why astronomers often call nebulae stellar nurseries. The word is gentle, and it fits, for just as nurseries on Earth are places where many young lives begin side by side, so too are these vast clouds the cradles where stars are born together in clusters. A single nebula can be dozens or even hundreds of light years across, large enough to hold within it the seeds of thousands of future suns. Inside, gravity does not act only on one patch of gas. It works on many at once, pulling countless little knots into being. As the whole cloud stirs and collapses, different parts of it reach the right conditions at different times, so across the nebula, protostars form almost in chorus. Some are close together, their disks overlapping, their jets sometimes crossing paths. Others are scattered farther apart but still children of the same mist. To the outside observer, if they could see with the right instruments, the nursery would appear as a glowing region of colour, with ribbons of pink and red from hydrogen gas lit by nearby stars, and deeper shadows where dust hides the light. These glowing patches are not just beautiful to the eye, they are signals that new stars are stirring within. Famous regions such as the Orion Nebula, the Eagle Nebula, or the Carina Nebula show this process frozen in time, clouds filled with thousands of newborn stars, each at a different stage, some still hidden, some already shining bright enough to illuminate their siblings. Stars are rarely born alone, because the collapse of a nebula is not a single event but a widespread process. When one region begins to form a protostar, the turbulence it creates ripples through nearby gas, making other clumps gather. When the first young stars ignite, their radiation and winds push on the surrounding dust, compressing it and triggering further collapses nearby. In this way, the birth of stars comes not as a single isolated moment, but as a chain reaction that sweeps through the cloud over millions of years. For this reason, most stars we see in the sky began life with brothers and sisters, born at the same time in the same cloud under the same conditions. Even our Sun is thought to have had siblings, long since scattered across the galaxy. These siblings may now be thousands of light years away, indistinguishable to the naked eye, but their atoms once rested in the same cradle. This grouping has consequences. When stars are born together, they influence one another's growth. A massive star in the cluster, burning hot and bright, sends fierce winds into the surrounding gas, shaping the development of nearby smaller stars. In some cases, the larger stars even end their lives in powerful explosions, enriching the gas with heavy elements that later become part of forming planets. Thus, the nursery is not only a place of birth, but also a place of interaction, where the destinies of stars are woven together. Picture it as a vast cosmic forest, with young trees sprouting in groups, their roots intertwined, their growth shaped by those around them. A nebula is a forest of stars in the making, and its beauty lies not only in its colours and shapes, but in the quiet truth that stars are social in their origins. They emerge from the same clouds, grow up in the same clusters, and only later drift apart into the galaxy. When we look at the night sky, we're not seeing solitary lives scattered randomly. We're seeing the scattered remnants of ancient families, stars that once shared the same cradle, but now wander far from one another. The nebula remains behind, thinned and dispersed, its gas consumed or blown away, but its legacy continues in the stars it has released. In this way, stellar nurseries remind us that creation is rarely lonely. It is collective, it is shared, and it is woven into the fabric of space like threads spun together into a single cloth. And within these cradles, as the dust settles and the first young stars begin to shine, The moment finally approaches when a protostar ignites the spark that turns it into a true star, marking the next chapter in this long story of cosmic birth. At the heart of the protostar, after millions of years of slow gathering, the temperature and pressure rise to levels that are difficult to imagine. The gas that was once thin and scattered across light years is now pressed so tightly together that each atom is almost shoulder to shoulder with its neighbours, unable to move freely, colliding again and again in an endless storm. With each collision, the core grows hotter, climbing from thousands of degrees to millions. This is no longer the gentle warming of a cloud under compression. This is the forging of fire. When the core reaches around 10 million degrees, something extraordinary happens. The hydrogen atoms that make up most of the protostar, each with a single proton at its centre, are forced so close together that their natural repulsion is overcome. Under normal conditions, these particles resist being near one another, like two magnets with the same pole pushed together, but under immense heat and pressure, gravity presses them so tightly that they fuse into something new. Two hydrogen nuclei merge into helium, and in the process, a small part of their mass is transformed into pure energy. That releases nuclear fusion, and it is the defining moment of a star's true birth. Fusion is simple to describe, yet immense in its consequences. It is the same process that powers hydrogen bombs, but in stars it is steady, controlled, and patient, unfolding not in seconds but across billions of years. Each fusion reaction gives off energy, and that energy radiates outward from the core, pushing against the inward pull of gravity. At last, the two great forces find balance. Gravity presses inward, always trying to collapse the star, but the energy from fusion pushes outward, creating a stable equilibrium. The star no longer shrinks, no longer struggles against its own weight. It shines steadily, its structure held in perfect balance by the constant flow of fusion at its heart. From the outside, what was once a hidden protostar wrapped in dust now clears the cocoon away with the power of its light and wind. It emerges into the galaxy as a shining new star, sending out its first rays into the surrounding darkness. The birth is complete. If we could watch it from nearby, we would see the surrounding cloud glow as the newborn star illuminates the gas, sculpting the nebula into new shapes, sending ripples of energy through its siblings. The star's disk remains, a wide ring of material orbiting the bright centre, waiting to form planets, but the central object has crossed the threshold that marks true existence. This is no longer a protostar. It is a star in every sense, a beacon powered by fusion, a furnace that will continue burning steadily for millions, billions, or in some cases trillions of years. Our own sun experienced this moment about 4.5 billion years ago. Before that, it was only a protostar, glowing faintly in the dark, but once fusion began, it became the stable star we know today. Fusion is the great engine of the universe. It takes the simplest element, hydrogen, and through patient burning transforms it into helium, then into heavier elements as stars grow older, building the periodic table piece by piece. But at this stage, in the youth of a star, hydrogen into helium is enough. The balance has been struck. The star has found its rhythm. It will now spend the majority of its life in this steady state, shining quietly, feeding the galaxy with light. In this way, the spark of fusion is not only a beginning, but also a promise. It is the moment when the star becomes stable, when its life truly begins, when the silence of the nebula gives way to the steady hum of light that will endure across cosmic time. And with that hum, the story shifts from fragile birth to the long journey of a star's life. When a star first begins the steady rhythm of fusion in its core, it does not instantly become calm and perfectly balanced. The early years of a star's life though measured in millions of years, are a time of adjustment, of testing boundaries, of learning to hold steady against the forces that shape it. These are sometimes called the T Tauri years, named after a young star in the constellation Taurus that shows these restless qualities. In this stage, the star is still shedding the last of the material that formed it, still drawing in gas from its surrounding disk, still pushing away dust with the powerful winds it now produces. The balance between gravity pressing inward and the outward pressure of fusion is close, but not yet perfect, and the result is a star that flickers, brightens, dims, and pulses unpredictably. To distant eyes it may appear as though the young star is playing, its light unsteady, like the flicker of a candle before it steadies into a flame. This instability is natural, for the star is still regulating its core, adjusting the delicate equilibrium that will sustain it for most of its lifetime. The outer layers churn with convection, giant streams of hot gas rising and falling in rolling currents, carrying heat outward in irregular patterns. Magnetic fields twist and snap, creating sudden flares that erupt into space, bursts of energy that can travel for billions of kilometers. Sometimes streams of matter shoot away from the star in narrow jets, reaching far beyond the surrounding disk, carving channels through the nebula. All of these behaviors make young stars unpredictable neighbors, restless children of the cosmos, filled with energy but not yet disciplined. And yet, for all their turbulence, these early years are essential, for through them the star clears away its surroundings, sweeping its disk, blowing away the leftover gas, and beginning to define the environment that will one day host planets. If you could drift near such a star, it would be both dazzling and chaotic. The light would flash and shimmer, the winds would blow with unimaginable force, and the surrounding nebula would be stirred into intricate patterns by the energy pouring outward. But over time, the star settles. The flickering becomes less extreme. The brightness steadies, though not completely. Even our own sun, in its first 100 million years, would have been more unstable, more variable, more active than it is now, sending out stronger winds and more frequent flares. In these early years, a star is like a musician learning the first notes of a song, sometimes off rhythm, sometimes too strong, sometimes too weak, but slowly discovering the pattern that will carry it through the long performance of its main life. Planets forming in the surrounding disk must weather this restless stage, bombarded by radiation, stirred by turbulence, shaped by the irregular flows of energy. Some disks break apart under the strain, their material blown away into space, leaving little behind. Others endure, their dust clumping together, forming rocks, then worlds, which will orbit the star for billions of years to come. The early star years are playful, but they are also decisive. They mark the shift from fragile beginnings to a more stable existence, and the changes that occur here determine whether the system will grow into one with planets, moons, and perhaps even life, or whether it will remain barren, a single star shining alone. And though the star itself seems restless, its destiny is already clear. The turbulence will pass, the flickering will calm, the winds will settle, and the star will enter the long, stable phase that defines most of its existence. But before we arrive at that chapter, we must linger here for a moment in the playful years when the star is still learning, still flickering, still adjusting, before it finally finds the balance that will allow it to shine with steady light for billions of years. When a young star finally overcomes its flickering years and learns to balance the inward pull of gravity with the outward push of energy from its core, it enters what astronomers call the main sequence, and this is the stage where it will spend almost all of its life. If the early stages were restless childhood, then the main sequence is a kind of cosmic adulthood, steady, reliable, and quietly enduring. the forces inside the star reach a near-perfect equilibrium. Gravity, always pressing inward, is balanced exactly by the pressure of nuclear fusion pushing outward, and this balance can last for billions or even trillions of years depending on the size of the star. In this state, the star shines with a steady brightness, no longer flickering like a candle but burning like a lamp with a constant glow. Our own sun is in this stage now, fusing hydrogen into helium deep within its core, turning mass into energy every second in amounts beyond imagination. Each second, about 600 million tons of hydrogen undergo fusion, releasing light and heat that spread outward through the solar system, illuminating Earth, warming its oceans, driving its winds, and making life possible. And yet, even with this vast consumption, the sun has enough fuel to continue for billions more years before this balance begins to change. To us, a star on the main sequence seems eternal, but it is simply patient. The timescales are so large that human history, human civilization, even the whole of human existence, is nothing more than a blink compared to the star's steady burning. If you looked at the sun through ancient eyes thousands of years ago, it would have seemed no different than it does now, and if humanity looks again thousands of years into the future, it will appear the same still, unwavering, calm and constant. Stars on the main sequence come in many sizes and colours, and those differences decide how long their adulthood lasts. Small stars, called red dwarfs, are dim and cool, using their hydrogen fuel very slowly. They can live for trillions of years, far longer than the universe has even existed, which means that no red dwarf has yet lived long enough to die. They shine faintly, barely visible to the naked eye from Earth, but they are by far the most common type of star in the galaxy, filling the Milky Way with quiet, enduring light. Medium stars like our Sun live for billions of years, long enough for planets to form, for life to arise, for civilizations to look up and wonder where they came from. And then there are the massive stars, hot and blue, which burn with incredible brilliance but at an enormous cost. Their fusion is so intense that they use up their fuel in only a few million years, a brief flash compared to the lifetimes of smaller stars. Their light is dazzling, their presence powerful, but their lives are fleeting. Regardless of size, the main sequence is the defining stage of stellar existence. This is when the star is most stable, most productive, most like what we imagine when we think of a star. It is the time of quiet work, of endless transformation, of turning simple hydrogen into helium, building the elements that will one day become part of planets, part of oceans, part of living beings. When we look at the night sky, nearly every point of light we see is a star in its main sequence, shining steadily across the darkness, their light travelling for years, centuries, or millennia to reach our eyes. To imagine this stage is to imagine constancy. The star does not hurry, does not waver, does not falter. It simply shines, day after day, year after year, age after age, until whole galaxies have shifted and spun around it. It is this constancy that allows the slow unfolding of other stories. Planets orbit steadily in the warmth of their parent stars. Life has time to emerge, to adapt, to grow complex. Civilizations like ours have time to wonder about their place in the universe. All of this is possible only because main sequence stars hold their balance so well, burning evenly and faithfully across unimaginable spans of time. This is why the main sequence is not just another stage of stellar evolution, but the very heart of it, the chapter that defines a star's identity more than any other. And though it seems unchanging, the process is always moving forward, hydrogen slowly turning into helium, the balance slowly shifting, the star quietly aging even as it appears timeless. One day the balance will break, the fuel will thin, the star will change, but that lies far in the future. For now, in the long calm of the main sequence, the star shines as though it will shine forever, its light steady against the darkness, its presence a quiet promise written across the sky. Among the stars that find their balance on the main sequence, none are more patient, more enduring, or more quietly persistent than the smallest of them all. These are the red dwarfs, stars with masses only a fraction of our sun's, often half its size or less, sometimes barely above the minimum weight needed to ignite fusion at all. Because they are so small, their pull of gravity is weaker, their cores are cooler, and their burning is slow and gentle. Instead of racing through their hydrogen supply, they sip at it carefully, stretching it across timescales that are almost impossible to imagine. While a star like our Sun lives for about 10 billion years in the main sequence, a red dwarf can live not just billions, but trillions of years, 10 trillion years times, 100 times, even 1,000 times longer. This means that in the entire history of the universe, which is about 13.5 billion years old, not a single red dwarf has yet had time to run out of fuel. Every one of them that has ever formed is still burning, still glowing, still alive today, scattered across the galaxy like countless quiet embers. To the naked eye, red dwarfs are difficult to spot. They are small and faint. Their light dim, their glow reddish rather than bright white. Most are invisible without telescopes, and yet they are the most common type of star in the universe. For every hot, dazzling blue star that burns out in a few million years, there are hundreds of red dwarfs shining faintly, unnoticed, but destined to last longer than almost anything else in existence. Their lives are uneventful compared to the giants. They do not flare into brilliant explosions. They do not swell into supergiants. They do not collapse violently. Instead, they remain steady, quiet, faithful, their hydrogen burning slowly and evenly, their glow constant. A red dwarf uses its fuel so efficiently that it mixes the hydrogen throughout its interior, unlike larger stars that only fuse hydrogen at their cores. This means that a red dwarf can use nearly all of its hydrogen, wasting nothing, stretching its lifetime as far as physics will allow. The result is a life so long that when the universe itself grows old, when galaxies have changed their shapes, and many other stars have already burned out and gone cold, red dwarfs will still remain, glowing softly in the fading dark. For planets that orbit them, this stability can be a gift. A small world circling a red dwarf might remain in its warmth for hundreds of billions of years, far longer than Earth will enjoy the steady light of the sun. But life around such stars faces challenges too, for red dwarfs, though stable in the long term, can sometimes unleash powerful flares, bursts of energy that would sweep across their planets. Even so, their persistence makes them perhaps the most enduring beacons in the galaxy. To think of a red dwarf is to think of patience made visible, a light that asks for nothing, a star that is content to glow quietly without spectacle. If the large stars are fireworks, brief and brilliant, then red dwarfs are the embers of a hearth fire, glowing steadily through the longest of nights. And when all other stars have burned out, when the galaxy itself has changed beyond recognition, red dwarfs will still be there, the last lights of the cosmos, fading only after trillions of years of quiet endurance. In this way, small stars remind us that brightness is not everything. The universe values persistence as much as spectacle, patience as much as power, and the faint glow of a red dwarf, though humble, will outlast the brilliance of every giant. It is in these quiet lives that the story of the stars finds its longest chapters, chapters that stretch beyond human comprehension, reminding us that in the silence of space, endurance is its own kind of greatness. While the smallest stars live quietly for ages beyond counting, the larger stars live in a completely different way, their lives marked by brilliance and intensity rather than patience. A massive star begins its life with a great burden, its enormous size. With 10, 20, 50 or even 100 times the mass of our Sun, gravity presses down on its core with a strength so great that the only way to resist collapse is for fusion to rage at a furious pace. Instead of carefully burning through its hydrogen fuel, as a red dwarf does, a giant star burns through its supply with astonishing speed, consuming in a few million years what might last a smaller star for tens of billions. This frantic pace gives them a glow that is dazzling beyond measure. A massive blue-white star can shine with hundreds of thousands of times the brightness of the Sun, outshining whole clusters of smaller stars combined. To the eye, they dominate the regions where they live, their light carving through the darkness of their nebulae, their heat and radiation altering the shape of the clouds around them. These are the stars you see blazing from far away in constellations, the ones whose brilliance crosses vast distances to reach our planet. But while their light makes them seem eternal, their lives are fleeting. A few million years may feel endless to us, but in the language of the cosmos it is only the blink of an eye. These stars are like fireworks, stunning, powerful, unforgettable, but gone before you have time to fully grasp them. Their impact, though brief, is enormous. The radiation they pour into space sculpts their surroundings. Their intense stellar winds blow outward with unimaginable force, clearing away dust and gas, shaping the cradle of their birth into intricate forms, and often triggering the collapse of nearby material that forms new stars in turn. In this way, they act as both destroyers and creators, tearing apart some regions even as they encourage the birth of others. Yet for all their beauty and influence, they are not gentle. Planets that orbit close to them, if they form at all, endure floods of radiation so fierce that their surfaces are stripped bare. The environment near a giant star is unstable and unforgiving, leaving little room for the quiet processes that allow life to emerge. Their role is not to nurture, but to blaze, to change, to forge. Inside, their cores tell an even more dramatic story. In smaller stars, hydrogen fuses steadily into helium for billions of years. In giants, this phase is short. Soon, helium begins to fuse into carbon, carbon into oxygen, oxygen into neon, and so on, building layer upon layer of heavier elements like the rings of an onion. Each layer burns hotter and faster than the one before, until the entire star is a furious workshop of nuclear reactions. In this way, the giants are responsible for forging nearly all the elements heavier than helium, the very materials that later become part of planets, part of rocks, part of water, part of living creatures. Every atom of iron in your blood, every atom of calcium in your bones was made in the heart of a massive star long before Earth existed. Yet this work comes at a cost, for each new step in fusion consumes fuel faster, destabilizing the star further. As the layers build and burn, the balance becomes harder to maintain, and the core grows ever closer to collapse. The outer layers swell, turning the star into a red or blue supergiant, so large that if it replaced our Sun, its surface could reach beyond the orbit of Mars. To stand in its presence, if such a thing were possible, would be to see a sky filled entirely by fire, a horizon with no darkness, only the endless brilliance of a star that has grown to engulf nearly all it touches. But this grandeur does not last. The same forces that make giant stars so bright also make them unstable, and their lives end far sooner than those of their smaller siblings. They blaze fiercely. They give the galaxy its heaviest elements. They shape their environments with radiation and wind, and then they die young, their cores collapsing in violence, their outer layers cast into space, their brilliance replaced by silence. That ending will come soon in cosmic time, and when it does, the death of a giant will be one of the most powerful events in the universe. For now, it is enough to see how their lives differ from the quiet endurance of the smallest stars. Where a red dwarf is an ember that can glow almost forever, a giant star is a flame that burns too hot and too fast, dazzling but doomed. Together they form a contrast that defines the story of stellar life. Patience versus intensity, endurance versus brilliance, the soft glow of small stars against the fierce blaze of giants, and it is. Within this contrast that the universe writes its balance, for both kinds of stars, long-lived and short-lived, have roles to play, each shaping the cosmos in its own way. Inside every star, whether small and steady or large and short-lived, the true work of its life takes place not on the surface we can see, but deep in its hidden core, where pressures are unimaginable and temperatures reach into the millions. Fusion is the process at the heart of this story, and though the word sounds technical, the idea is simple. Atoms, which are the tiny building blocks of matter, do not normally like to come too close. Each carries a positive charge, and like magnets with the same pole they repel each other. But when the heat and pressure inside a star are great enough, those repulsions can be overcome. At that point the atoms fuse, or join, into something new, releasing energy as they do so. In young stars like our Sun, the main task is the fusion of hydrogen, the simplest atom, into helium. You can imagine hydrogen as the smallest puzzle piece, light and simple, and helium as a slightly larger puzzle piece, built from 4 of those hydrogen blocks pressed together. Every time this puzzle is completed, a small bit of mass is converted into energy, and this energy streams outward as the light and warmth that we see and feel. This process is steady and efficient, and it is what allows stars to remain stable for so long. But in larger stars, once the hydrogen in the core begins to run low, fusion does not stop. Instead, the star changes gears and begins fusing helium into carbon, and carbon into oxygen, and oxygen into neon, building heavier and heavier elements in its core. The process is like an onion being built from the inside out. In the very centre lies the hottest and densest region, where the newest and heaviest elements are formed, while outside it, in successive shells, lighter elements are still fusing. Hydrogen burns into helium in one layer, helium burns into carbon in another, carbon into oxygen in another, each layer feeding the one above it with new material. It is a quiet assembly line of creation, a workshop hidden deep within the star, forging the elements that will one day be scattered into space. To understand the timescales, imagine that while hydrogen can burn steadily for billions of years, helium might last only millions, carbon perhaps only thousands, and the heavier stages only years or even days. The more advanced the fusion becomes, the faster it runs, until the star is racing toward its end. And yet, even in this furious pace, the work is monumental. Nearly every element heavier than helium in the universe was built in the core of a star, from the carbon that forms the backbone of life to the oxygen we breathe, the silicon in rocks, and the iron that carries oxygen in our blood. When you look around at the world, when you hold something in your hand, when you breathe in and out, you're experiencing the quiet results of fusion that happened long before Earth even formed. In small stars, this process ends with helium. In medium stars like the Sun, it goes as far as carbon and oxygen. In massive stars, it races through the periodic table, building heavier and heavier elements until it can go no further. The limit is iron, for fusing iron does not release energy, it consumes it, and once a star builds an iron core, it has reached the end of its creative work. From that point, the balance breaks, and the star faces collapse. But long before that ending, the hidden work of fusion has already filled the galaxy with the ingredients needed for life and planets. This work is quiet, invisible, and patient. It is not the bright surface we see, but the unseen labour at the heart of every star, the silent furnace that turns the simplest element into the complexity of a universe. And as we drift deeper into this story, we follow that path toward the moment when balance finally begins to fail, when the fuel runs low, and when the steady glow of a star gives way to the changes of its aging years. For so long a star lives in quiet balance, its gravity pulling inward while the energy from fusion pushes outward, the two forces locked in harmony so perfect that the star seems timeless. But slowly, inevitably, the balance begins to fail. Deep in the core, hydrogen fuel is being consumed, one fusion reaction at a time steadily transformed into helium. At first, the change is subtle, for the star has so much hydrogen that it burns steadily for millions or billions of years, depending on its size. Yet as time passes, the helium ash builds up, taking the place of the hydrogen in the very heart of the star. The core is now filled with material that will not fuse under the same conditions, and as the supply of hydrogen shrinks, the amount of outward energy falls. Gravity, ever patient, takes its opportunity. The core begins to contract, its weight pressing down more heavily than before. This shrinking raises the temperature and pressure even higher, and in response the thin shells of hydrogen that remain around the core ignite in bursts, fusing more quickly, producing more energy. But this is not the steady rhythm of the main sequence. It is unstable, uneven, like the beating of a heart under strain. The star begins to change on the outside as well. No longer a steady yellow or white, its surface swells outward. The outer layers, now pushed by surges of energy from within, expand into space. The surface cools as it stretches, and the star takes on a redder hue, becoming what we call a red giant. For stars much larger than our Sun, the expansion is even greater, and they swell into red or blue supergiants, luminous and vast, their size dwarfing whole planetary systems. To imagine this change is to picture the Sun, now modest in its golden glow, one day growing so large that it will engulf Mercury, Venus, and perhaps even Earth, its surface glowing red, its size hundreds of times greater than it is now. To us this fate lies billions of years in the future, but to the universe it is an ordinary part of a star's life cycle, as predictable as the rising and setting of the sun each day. As the core contracts, new stages of fusion begin. Helium, under the new pressure, ignites into carbon and oxygen, often in sudden flashes of energy that ripple outward. These flashes cause the outer layers to pulse, expanding and contracting, brightening and dimming. A once steady star now flickers and changes, its light no longer constant but restless, reflecting the struggle taking place inside. In massive stars the process moves even faster, the layers burning heavier and heavier elements in sequence. Helium, carbon, oxygen, neon, magnesium, silicon, each stage shorter than the last, some lasting millions of years, some thousands, some only days. The star becomes like a layered furnace, each shell fusing a different element, its interior a turbulent onion of creation. But no matter the size, the message is the same. The balance that once defined the main sequence has broken. The outward pressure of fusion cannot keep up with the inward pull of gravity forever. For small stars, this means a slow swelling, a shedding of outer layers, a gentle fading. For large stars, it means instability, collapse, and eventually explosive endings. But in every case, the journey away from stability begins here, in the moment when fuel grows thin, when the steady light of youth gives way to the restless glow of age. A star that once seemed eternal now changes visibly over cosmic time. To human eyes, it might still appear steady, but in the grand span of millions of years, the difference is dramatic. The sky that looks fixed and timeless to us is always shifting, always aging, always moving toward transformation. And so, when balance breaks, the story of a star enters its final chapters, magnificent, unstable, and fleeting, carrying it toward the stage of giants that glow bright in their final years before fading away. When the balance in a star finally slips and its core contracts while its outer layers respond by expanding, the star enters one of the most dramatic and visible stages of its life. A once steady, modest star like the Sun swells outward until it becomes a red giant, while stars many times more massive become red or even blue supergiants, glowing with a scale that almost defies imagination. This change is slow on human terms but swift on cosmic ones, unfolding over millions of years, a heartbeat in the life of the galaxy. The core, now burning helium into carbon and oxygen, is small, dense, and incredibly hot. But the outer layers are extended, thin and cool, which gives the star its reddish glow. For a medium star like our Sun, this swelling can reach such an extent that the star's surface will stretch beyond the orbit of Mercury, then Venus, and perhaps Earth itself. If Earth survives, the sky would be filled entirely with the blazing surface of our swollen Sun, the horizon consumed by its fiery red expanse. For larger stars, the swelling is even greater. A supergiant can reach a size so large that if it were placed in the centre of our solar system, its surface would extend past Jupiter's orbit. Imagine a star so immense that it could contain hundreds of millions of suns inside its volume, and yet despite this size, its outer layers are fragile, tenuous, and unstable, like a great balloon ready to burst. In this phase, the star shines with immense brightness, sometimes tens of thousands or even hundreds of thousands of times more luminous than the Sun, and its light can be seen across the galaxy. To astronomers, these stars are among the most striking objects in the night sky, and many of the bright stars visible to the naked eye, such as Betelgeuse in Orion, are red supergiants nearing the end of their lives. The surface of such stars is restless, marked by convection currents that span millions of kilometers. Hot gas rises and falls in vast loops, creating enormous star spots, dim patches larger than Earth itself. The star pulses, expanding and contracting slowly, its brightness changing over time as it struggles to maintain a balance that can no longer hold steady. In some cases, strong stellar winds blow away the outer layers, sending material drifting into space, forming glowing shells of gas around the star. These winds enrich the surrounding nebula with the elements the star has created, preparing the way for future generations of stars and planets. For massive stars, the process inside is even more intense. The core continues fusing heavier and heavier elements in rapid succession, each stage shorter than the last, until the star is layered like an onion, with shells burning hydrogen, helium, carbon, oxygen, neon, and silicon, all at once. This furious activity cannot last, and though the outer appearance is one of grandeur, the inner reality is that the star is racing toward collapse. Yet from a distance, what we see is the glory of its swelling. A star that was once a faint dot becomes a beacon, its size and brightness magnified beyond recognition. It becomes a monument in the sky, a signal of age and impending transformation, a reminder that even the mightiest of stars do not endure unchanged. Red giants and supergiants are beautiful, not in the fragile way of youth, but in the magnificent, oversized way of endings. Their glow is softer, redder, their light more diffuse, but their scale is overwhelming, filling the skies of nearby worlds, illuminating the nebulae around them, reshaping their environments. This stage does not last long compared to the main sequence, but it is among the most spectacular. For the Sun, the red giant phase will mark its final visible glory before it sheds its outer layers and leaves behind only a core. For supergiants, this swelling is the prelude to a far more violent ending, a collapse and explosion that will scatter their material across the galaxy. But before that ending, there is this swelling, this magnificent transformation, when a star grows to fill a space far greater than its beginnings, shining as one of the most luminous objects in the universe, a cosmic giant nearing its farewell. For the smallest and most modest of stars, the story of their ending is not written in fire and violence, but in softness, in release, in a long and graceful farewell. A star like our Sun spends billions of years in the calm balance of the main sequence, fusing hydrogen into helium, holding its shape against the endless pull of gravity. But eventually, even for such a steady star, the fuel deep in its core grows thin. Hydrogen is consumed, helium builds up, and the balance begins to wobble. The star swells into a red giant, its outer layers stretching across space, its light shifting to a cooler red as its surface expands. This swelling is dramatic, yet it is not the final act. Deep inside, helium begins to fuse into carbon and oxygen, but even this cannot last forever. When that helium too is exhausted, the star cannot ignite the heavier elements. Its mass is simply too small, its core never hot enough to take the next steps that only giant stars can manage. And so, at this stage, gravity wins its quiet victory. The core contracts into an incredibly dense ember, while the outer layers, expanded, fragile and barely held, begin to drift away. They are released not in one sudden burst, but in waves, like a long exhalation, the star letting go of what it no longer has the strength to keep. These layers, made of gas and dust, drift outward into space, illuminated by the light of the hot core left behind. From afar they appear as glowing shells of soft colour, delicate and intricate, the shapes sculpted by the forces of the dying star. Astronomers call these structures planetary nebulae, not because they have anything to do with planets, but because early telescopes made them appear like faint disks, reminiscent of planetary shapes. In truth, they are the star's final blossoms, luminous flowers unfolding into space. Some appear as perfect rings, glowing circles against the black. Others take on ovals, or more complex forms, shaped into wings, arcs, or butterfly-like symmetry by the winds and fields of the star. Each is unique, each a brief but breathtaking moment of beauty, lasting only tens of thousands of years, a blink in cosmic terms, before dispersing into the wider galaxy. At the centre of this glowing cocoon rests the star's true remnant, a white dwarf. This core is astonishing in its density. It may be no larger than Earth, yet it holds as much mass as the Sun. The matter inside is so tightly packed that a teaspoon of it would weigh tons upon tons, far heavier than anything imaginable on our planet. And yet, despite its density, the white dwarf shines faintly, glowing not because it continues to fuse elements, but because it is still radiating the immense heat left over from its long history. Over billions of years it will cool, its light dimming slowly, almost imperceptibly. Eventually it will become a cold, dark object, what astronomers sometimes call a black dwarf, though the universe is not old enough for any star to have reached that stage yet. For now, every white dwarf ever formed still glows somewhere in the darkness, a quiet ember, a star's memory etched into the night. For planetary systems orbiting such stars, the transformation is profound. Inner planets are often consumed during the red giant phase, their material added to the expanding atmosphere, but outer planets, asteroids and comets may survive. They continue their orbits, circling now not a bright sun but a faint white ember, their skies lit only by the ghost of what once was. If life ever existed there, its fate is sealed, for the warmth that sustained it fades, leaving cold and stillness. And yet this soft farewell is not an end without meaning. The gas and dust shed into space do not vanish. They enrich the galaxy, seeding future clouds with carbon, oxygen, nitrogen, and other elements that small stars create during their lives. That material will drift, mix, and eventually become part of new stars, new planets, new oceans, new beings. In a very real sense, the death of a small star is the gift of its body back to the cosmos, the scattering of the pieces it has forged so they may one day build something new. Our own sun will follow this path billions of years from now. It will swell into a red giant, shed its outer layers, and leave behind a glowing planetary nebula, a jewel of light in the dark, with a white dwarf at its heart. That nebula will drift apart over time, its gases lost to the galaxy, but for a brief span it will shine as a final, beautiful statement before fading into the silence. The sun's white dwarf will then glow faintly, cooling for eons, carrying the memory of all that came before. And though this ending may seem quiet compared to the violent deaths of massive stars, there is a profound poetry in it. Small stars do not go out in explosions, they go out in whispers, in gentle light, in soft clouds that remind us endings can be beautiful too. At the centre of a planetary nebula, after the outer layers of a small star have drifted away into glowing shells, what remains is the white dwarf, a remnant that carries the memory of its star's long life. A white dwarf is tiny compared to the star it once was, no larger than Earth, but it holds within it a mass equal to or greater than the Sun. This density is difficult to imagine. Matter inside a white dwarf is packed so tightly that a teaspoon of it would weigh tons upon tons, more than mountains on Earth, compressed into a single fragment. And yet, for all its weight, a white dwarf is quiet. No longer does fusion roar in its heart. It has no fuel left to burn, no energy to generate beyond the heat it still holds from its past. What we see is the glow of that stored heat, slowly radiating into space. At first, the white dwarf shines brilliantly, its surface searingly hot, glowing blue-white. Over millions of years it cools, its colour shifting from blue to white, from white to yellow, then to red, and eventually to darkness. This cooling is an extraordinarily slow process, stretching across billions of years, longer than the age of our universe itself. Because of this, no white dwarf has yet had time to cool completely. Every one that has ever formed since the first stars died still glows faintly, scattered across the galaxy like embers that refuse to fade. But one day, in a future so distant it defies imagination, they will cool entirely. A white dwarf will eventually become a black dwarf, a dark, cold remnant of matter, invisible against the backdrop of space. None exist yet, for the universe is not old enough, but they are written into its future, waiting at the end of time. In this fate there is a stillness that is unlike anything else in the life of a star. There are no eruptions, no explosions, no sudden changes. The cooling happens gradually, imperceptibly, so that even over millions of years the star seems hardly different. It is as if the cosmos has placed these remnants into a deep sleep, a sleep so long that it may last until the universe itself changes in ways we cannot yet imagine. White dwarfs are reminders of endurance, of quiet persistence. They may no longer burn, but they still carry the story of fusion, of light, of all the elements they once forged and scattered. They shine not with new fire, but with the warmth of memory, the leftover heat of their younger years. And though they fade, the fading is graceful, a slow surrender to the cold, a patient dimming into the background of time. If you were to orbit one of these stars, your sky would be dark and quiet, the central glow faint, the warmth minimal. Yet in that faintness is a kind of peace. The violence of creation and the turbulence of youth are gone. What remains is calm, still, enduring. Our own sun will follow this path. After it becomes a red giant and releases its outer layers, its core will shrink into a white dwarf, glowing fiercely at first, then cooling for billions upon billions of years. Long after Earth is gone, long after the Milky Way has shifted its shape, the sun's white dwarf will still glow faintly, an ember of what once was, holding silently to the last fragments of heat before becoming dark. This fate is quiet, but it is not empty, for the light that once came from that star will already have filled the universe. The elements it created will already have joined new clouds, formed new stars, built new planets, and perhaps even new lives. In this way, the quiet fate of white dwarfs is not an end but a resting place, a reminder that even as they fade into silence, their contributions remain scattered across the galaxy. The star is gone, but its story continues in everything that follows. For the larger stars, the ending of life is not quiet or gentle, but sudden and overwhelming, a farewell that shakes the very fabric of the cosmos. While a smaller star like our Sun will never grow hot enough to fuse elements heavier than carbon or oxygen, a giant star continues far beyond that, layering its interior like an onion, each shell fusing a heavier element than the one outside it. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, oxygen becomes neon, neon becomes magnesium, magnesium becomes silicon, and finally at the very centre, silicon fuses into iron. But when iron is reached, the star meets its limit. Iron cannot be fused into heavier elements without costing energy, and so fusion stops. The furnace that once pushed outward against gravity is gone, and gravity, always patient, finally wins. In less than a second, the star's core collapses inward. The atoms themselves are crushed, protons and electrons forced together to form neutrons, packing the matter into a density so extreme that a single teaspoon of this collapsed core would weigh billions of tons. The outer layers which were falling inward during the collapse slam into this dense new core and rebound, sending a shock wave racing outward. That shock wave, amplified by the flood of energy released in the collapse, tears through the star and blows it apart in a titanic event we call a supernova. To imagine a supernova is to imagine brightness beyond measure. For a short time, a single dying star shines more brightly than an entire galaxy of billions of stars. Light races outward, so bright that ancient people on Earth once saw new stars appear suddenly in the night sky, visible even in the day, only to fade weeks later. The energy released in that instant is greater than the Sun will produce in its entire 10 billion year lifetime. Yet for all its violence, the supernova is also an act of creation. In the intense heat and pressure of the explosion, new elements are forged: gold, silver, uranium, iodine, atoms that cannot be made in ordinary stellar fusion, but only in these final catastrophic moments. These elements, along with the carbon, oxygen, silicon and iron the star had already built, are thrown out into space, scattered across light years, mixing with gas clouds, enriching them, and ensuring that future stars and planets are made of more than hydrogen and helium. Without supernovae, there would be no iron in your blood, no calcium in your bones, no gold in rings or circuits, no heavy elements at all. Every atom heavier than iron inside us and around us was born in such an explosion, carried across space in the remains of stars that lived and died billions of years ago. For nearby space, a supernova is devastating. The blast can strip the atmospheres of planets, sterilize systems, and send shockwaves that compress interstellar clouds, triggering the birth of new stars even as others are destroyed. It is both destructive and creative, both an ending and a beginning, a reminder that in the universe, death and birth are often bound together. To witness a supernova safely would be to see the night sky filled with sudden light, a star outshining all its neighbours, growing brighter for days or weeks before fading slowly. To astronomers today, they are rare but precious events, opportunities to study the extremes of physics and to understand the cycle of matter. To life, they are the furnaces of origin, the reason complex chemistry exists at all. Once the light fades, once the expanding cloud of gas drifts outward into space, what remains at the centre is a transformed core. If the star was massive but not the largest, it leaves behind a neutron star, a dense, spinning remnant that we will visit soon. If it was truly enormous, its core collapses further still into a black hole, a place where gravity is so strong that not even light can escape. But before we reach those endings, we must rest here in the explosion itself, the spectacular farewell of a giant that lived quickly, shone brightly, and gave itself back to the universe in a blaze of light. The supernova is not simply death. It is the final act of generosity, the scattering of everything the star has built so that new worlds may one day exist. When a massive star dies in a supernova, the outer layers are scattered into space, but the very core does not simply vanish. What remains is a remnant so dense, so compact, that it challenges the imagination. If the star was not the most enormous of giants, its core does not collapse into a black hole, but instead stops at another state of matter, a neutron star. In these remnants, the collapse has been halted at the point where protons and electrons have been crushed together, leaving behind a body made almost entirely of neutrons. The result is an object only about 20 kilometers across, small enough to fit inside a large city, yet containing more mass than the Sun. The density is so great that a single teaspoon of neutron star material would weigh billions of tons, more than every mountain on Earth combined. To orbit such an object would be to experience gravity stronger than anything else short of a black hole. The surface is solid, the atmosphere only centimeters thick, the core unimaginably dense, and yet neutron stars are not silent. Many spin rapidly, rotating dozens, hundreds, or even thousands of times per second. These rapid spins come from the conservation of angular momentum, the same principle that makes a spinning skater turn faster when they pull in their arms. When the star collapsed from a radius of millions of kilometers to just a few kilometers, its rotation sped up enormously. A star that rotated once every few days as a giant can now rotate dozens of times in a second as a neutron star. Along with this spin come powerful magnetic fields, trillions of times stronger than Earth's. These magnetic fields channel streams of particles outward in beams of radiation. If those beams sweep past Earth as the star spins, we see them as pulses of light and radio waves, appearing and disappearing at regular intervals. These stars are called pulsars, and they are among the most precise timekeepers in the universe, their pulses repeating with astonishing accuracy, sometimes more consistent than atomic clocks. To observe a pulsar is to hear the heartbeat of a dead star, a steady rhythm ticking across the void, a lighthouse beam flashing again and again as the remnant spins. Some pulsars spin hundreds of times per second, their pulses arriving faster than the blink of an eye, their stability so great that astronomers use them as cosmic clocks to test the laws of physics. Though they are the corpses of stars, they are also laboratories, teaching us about matter under conditions we cannot recreate on Earth. The light from neutron stars can be faint, but their effects ripple far. Their strong gravity bends space around them. Their magnetic fields accelerate particles to near the speed of light, and their radiation can be detected across galaxies. For planets that might once have orbited the giant star, nothing survives nearby. The explosion of the supernova would have destroyed or ejected anything close. What remains is only the remnant spinning, flashing, cooling slowly over millions of years. In their quiet strangeness, neutron stars remind us that endings are not simple. The death of a giant star does not erase it, but transforms it into something new, something denser, stranger, and more extreme than what came before. These remnants, tiny yet massive, cold yet bright in pulses, carry on the story of the star in a different form. And while some cores stop here, others collapse even further, past the limits of matter itself, into black holes, where gravity becomes absolute. But before we fall into that final mystery, we linger with the neutron stars, the spinning lighthouses of the galaxy, the dense hearts of giants that continue to shine, not with steady light, but with rhythmic flashes that echo through space. When the most massive stars reach the end of their fuel and collapse, sometimes even the incredible pressure of neutrons packed together cannot resist gravity's relentless pull. In those cases, the collapse does not stop at a neutron star, but continues inward without limit. The matter falling into itself, compressed beyond anything we can describe with ordinary words. At the very centre lies what we call a singularity, a point of infinite density where our current understanding of physics breaks down. Around this hidden point is drawn an invisible boundary called the event horizon, the surface beyond which nothing can return. Light, travelling at the fastest speed allowed in the universe, cannot escape once it crosses this boundary. That is why we call these objects black holes, not because they are empty, but because they are sealed, dark, and final in their silence. They are the most extreme objects that nature creates, and yet they are born from the same cycle of star birth and star death that fills the galaxy with ordinary suns. A black hole can be surprisingly small in size compared to its mass. A black hole with the mass of our sun would be only a few kilometres across, while one with 10 times the mass of the sun might be no bigger than a city. To stand near its edge would be to face gravity so overwhelming that space itself bends steeply downward, as though reality itself had become a funnel. Time behaves strangely here. To a distant observer watching you fall, your movements would slow more and more as you approach the event horizon, your clock ticking more slowly compared to theirs, your image fading and stretching into red as the light struggles to escape. To you, however, nothing would seem different as you crossed the boundary, except that once you passed it, there would be no way back. Inside, all paths curve inward toward the singularity. We cannot see this place, and perhaps we never will, for no information escapes. It is a region cut off from the rest of the universe, its mysteries hidden forever behind the veil of the horizon. And yet, though we cannot look inside, we know black holes exist by the way they shape their surroundings. Gas and dust drawn too close form spinning disks around them, heating to millions of degrees as they spiral inward, glowing in X-rays that we can detect with telescopes. Powerful jets of matter and energy can blast outward along the black hole's poles, stretching across light years, shining like cosmic beacons. Stars orbiting nearby reveal invisible companions, their paths tugged by a massive object that emits no light. These clues are how astronomers find black holes, not by direct sight but by the footprints they leave behind. Black holes are not all the same. Stellar black holes formed from single stars are a few to dozens of times the mass of the Sun. In the centres of galaxies lie supermassive black holes, millions or billions of times the Sun's mass, their origins still uncertain, but their presence undeniable. Our own Milky Way has one at its heart called Sagittarius, a star, containing 4 million solar masses inside a region no larger than our solar system. Its gravity holds the galaxy together, guiding the motions of hundreds of billions of stars. Between these extremes may lie intermediate black holes, hundreds or thousands of solar masses, formed perhaps from clusters of stars merging. Each kind reminds us that the universe builds structures on every scale, from the smallest remnants to the most colossal anchors of galaxies. Though they are dark, black holes are not lifeless voids. They are engines, transforming matter into energy with efficiencies greater than any other process in nature. As material falls inward, it radiates more energy than nuclear fusion, glowing brightly before crossing the horizon. In this way, black holes, though invisible themselves, power some of the brightest phenomena in the universe. Quasars, among the most luminous objects ever observed, are driven by matter falling into supermassive black holes billions of light years away. To imagine such an object is to confront both mystery and beauty, endings and beginnings. For the death of a star into a black hole is not the erasure of its story, but another transformation, another link in the cycle of creation. The elements the star once forged are already scattered in space by earlier stages, building future worlds. What remains in the black hole is a reminder of limits, of places where our knowledge stops. It is a symbol of humility written into the universe, showing us that some questions may never be answered. Compared to the soft farewells of small stars or the rhythmic pulses of neutron stars, black holes are silent and absolute, gravity distilled into its purest form. And yet, even in their darkness, they play a role in shaping galaxies, in recycling matter, in fueling cosmic light. They are not emptiness, but presence, heavy and hidden, anchors of the universe that remind us of both the power of gravity and the fragility of stars. The death of a star, no matter how it happens, is never an ending in the absolute sense. Even in collapse, even in explosion, even in the quiet drifting away of outer layers, stars give themselves back to the universe in pieces that will one day form something new. This is one of the most profound truths in astronomy. We are not separate from the stars, but made of them, composed of the very atoms forged in their hidden furnaces. At the beginning, the universe was simple, filled only with hydrogen, helium, and traces of lithium from the Big Bang. Stars were the first to take these raw ingredients and through fusion build heavier elements. In their cores, hydrogen was pressed into helium, helium into carbon, carbon into oxygen, oxygen into neon, magnesium, silicon, and iron. In the explosions of the most massive stars, even heavier elements were formed: gold and silver, uranium and iodine, all created in the brief chaos of supernova. Each generation of stars enriched the galaxy further, scattering these new elements into space to be gathered by the clouds that would form the next generation. This is why planets like Earth exist, made not only of hydrogen and helium, but of rock, metal, water, and air. Our entire solar system was born from a cloud seeded with the remains of ancient stars, a mixture of dust and gas that had already lived many lives in other forms. The sun formed at its centre, and around it the leftover material flattened into a disk that built the planets. Earth came together from grains of dust rich in oxygen, carbon, silicon, and iron, all of it once carried in stars that lived and died long before. The oceans on Earth are filled with water whose hydrogen atoms date back to the birth of the universe and whose oxygen atoms were made inside stars. The calcium in your bones was forged in ancient stellar cores. The iron in your blood was built in a supernova billions of years ago. The gold in rings or circuits on Earth is the relic of explosions so bright they could outshine galaxies. To say that we are made of stardust is not a metaphor but a fact written into every cell. Each atom inside you carries the memory of a time when it was something else, when it burned inside a star, when it was part of a cloud, when it drifted in space waiting to become part of a new story. And when our own sun ends its life, the process will continue. Its outer layers will drift away, carrying carbon and oxygen into space. Those elements will one day mix with other clouds, form new stars and perhaps new planets. Perhaps far in the future, new beings will look up from those planets and wonder, as we do now, where they came from, not knowing that they carry within them the atoms of a long-vanished star like our sun. In this way, stars are never lost. They live on in every rock, every ocean, every living thing. The air you are breathing contains atoms forged billions of years ago in suns that have long since disappeared. The ground beneath you carries the remnants of explosions that shook the galaxy before Earth was born. You are, in the most literal sense, the universe made conscious, stardust that has learned to wonder about itself. And this cycle will not stop. The stars that exist today will die and scatter their gifts. The next generation will gather them, burn them, and scatter them again. Each cycle makes the galaxy richer, more complex, more capable of creating worlds like ours. The stardust we carry is not only a reminder of where we came from, but also a promise of continuity, of endless transformation. And as we drift deeper into this thought, we see that stars do not simply die. They change form, they give themselves away, they prepare the way for what comes next, leaving their light and their matter as the foundation for all future things. The story of stars is never a simple line from birth to death. It is a cycle that repeats again and again, weaving the history of the universe out of light, matter and time. When a star dies, whether it ends gently as a white dwarf or violently as a supernova, it scatters its elements into space. These atoms drift into interstellar clouds, mixing with gas and dust already floating between the stars. Slowly, patiently, gravity begins to draw the material together again, forming new nebulae, new stellar nurseries, new cradles where future stars will be born. In this way, every ending becomes a beginning. The clouds that give rise to new stars are not pristine. They are seeded with the remnants of those that came before. A red giant leaves carbon and nitrogen. A supernova adds iron, gold, uranium, and many other heavy elements. Together they enrich the cloud, ensuring that when it collapses into new stars and planets, those worlds are made of more than just hydrogen and helium. This enrichment is why Earth exists, why rocks, oceans, and living beings are possible. The universe began simple, but with every cycle it grows more complex, more capable of creating new forms. Imagine a vast nebula glowing faintly in the galaxy. Inside it are atoms from countless past stars, scattered and mixed beyond recognition. Some were forged billions of years ago, some only recently. Within the cloud, gravity begins its patient work, pulling clumps together, forming protostars that will ignite and shine. Around those stars, disks of leftover matter flatten and swirl, building planets, moons, comets, and asteroids. In time, some of those planets may carry water, and perhaps life, and perhaps even eyes that one day look up to wonder where they came from. In every sense, they will be the descendants of long-dead stars. Our sun is one such descendant. It formed about 4.5 billion years ago from a cloud enriched by countless supernovae, its light, its warmth, and every atom on Earth is part of that heritage. When it dies, its own contributions will join the galaxy, to be gathered into future clouds, to form stars and planets that may exist long after our own world is gone. And so the cycle continues. Stars are born, live, die, and return their matter to the galaxy, where it becomes the seed of new stars. Nothing is wasted, nothing is lost, only transformed. This rhythm is the heartbeat of the cosmos, slow and steady, measured not in years, but in billions of years, yet always moving forward. To look at the night sky is to see this cycle frozen at many different stages. Some stars are newborn, still wrapped in the gas of their nurseries. Others are in the long middle age of the main sequence, shining steadily for billions of years. Some are giants nearing their end, swollen and unstable. Others are already gone, their remnants scattered into nebulae that glow with borrowed light. The sky is a mosaic of beginnings, middles and endings, all happening at once, all part of the same repeating story. And through it, the galaxy evolves. The Milky Way today is not the Milky Way of billions of years ago, and billions of years from now it will be different still, shaped by the endless recycling of stars. In this way, the cosmos itself is alive with renewal, each death feeding a birth, each birth carrying the traces of what came before. The endless cycle of stars is not just a fact of physics, but a reminder of continuity, of patience, of the way time transforms everything yet wastes nothing. And as we follow this story to its final reflection, we carry the quiet knowledge that the stars above us, the stars within us, and the stars yet to be are all part of the same eternal turning of the universe. As we reach the end of this journey through the lives of stars, we can look back across the path we have followed and see the rhythm of the universe more clearly. It began with the silence of nebulae, clouds so vast and calm that they seemed almost empty, waiting for gravity to draw them together. Out of those clouds came clumps, small at first, then growing into protostars that glowed faintly in their cocoons of dust. We watched as fusion sparked, as stars began their long steady lives, shining for billions of years in quiet balance. We lingered with the smallest stars that live almost forever, glowing softly as patient embers, and we marvelled at the giants that blaze furiously and vanish quickly. We followed the hidden work of fusion as it built the elements that shape worlds, and we saw what happens when balance breaks, when stars swell into giants or collapse into explosions. We looked at the soft endings of small stars, the gentle release of their outer layers into planetary nebulae, leaving behind white dwarfs that glow quietly for eons. We listened to the pulses of neutron stars, the strange lighthouses of the galaxy, and we gazed into the mystery of black holes, where gravity grows so strong that not even light can escape. And then we returned to ourselves, to the stardust we carry, to the truth that every atom in our bodies was once part of a star. The carbon in our cells, the calcium in our bones, the iron in our blood, all of it was made long ago in stars that lived and died before our planet was born. Their endings became our beginnings. Their cycles became our inheritance. When you breathe, when you move, when you wonder about the night sky, you are participating in the story of the stars. And when our own sun reaches its end billions of years from now, it too will give its materials back to the galaxy, to be gathered into new clouds, to form new suns, new planets, and perhaps new lives. This is the endless cycle, the great turning of the cosmos, where nothing is wasted and nothing is lost, only transformed into new forms and new stories. To rest in this knowledge is to feel both small and vast at the same time. Small, because our lives are brief compared to the billions of years a star can shine. Vast, because we are made of the same matter, carrying within us the memory of the stars, woven into a universe that is old and patient and unbroken. Stars remind us that beginnings and endings are not opposites, but parts of the same flow. Their quiet lifetimes and their dramatic deaths both serve the same purpose, to keep the universe alive with renewal. And as you let these thoughts drift through your mind, you can allow them to soften, like starlight fading across the night sky. You do not need to hold every detail. You do not need to remember each stage. It is enough to feel the rhythm, the steady heartbeat of the cosmos, the reminder that everything is part of something larger, something ongoing, something eternal. The stars are teachers of patience. They burn steadily, unhurried, showing that time can be gentle and that change, though certain, need not be feared. They are teachers of humility, reminding us that even the brightest lives come to an end, yet nothing is wasted. And they are teachers of peace, showing that endings can be beautiful, that silence can be as meaningful as light. Tonight, as you rest, you can let that peace settle over you. The universe is vast, the stars are endless, and you are safe within their story. Their light continues to travel across the darkness, crossing years and centuries to reach your eyes, and in that light is the quiet reassurance that you belong to something that has always been and will always be. So let your eyes grow heavy, let your breath slow, let your body sink into rest. Imagine the stars above you, steady and calm, keeping their long watch. Imagine yourself drifting with them, patient, unhurried, part of the endless cycle. And as sleep comes, let the story of the stars carry you gently, reminding you that in every ending there is a beginning, in every silence there is renewal, and in every moment of rest there is a connection to the great and quiet universe that made you.